on that topic, I have to ask you about the paradox, the information paradox of black holes. What is it?
So, this is what catapulted Hawking's fame. When he was a young researcher, he was thinking about black holes and wanted to just add a little smidge of quantum mechanics, just a little smidge, wasn't going for full-blown quantum gravity, but kind of just asking, well, what if I allowed this nothing, this vacuum, this empty space around the event horizon? The star's gone, there's nothing there. What if I allowed it to possess sort of ordinary quantum properties, just a little tiny bit, nothing dramatic. Don't go crazy. And one of the properties of the vacuum that is intriguing is this idea that you can never say the vacuum's actually completely empty. We talked about Heisenberg, but the Heisenberg uncertainty principle really kicked off a lot of quantum mechanical thinking. It says that you can never exactly know a particle's position simultaneously with its motion, with its momentum. You can know one or the other pretty precisely, but not both precisely. And the uncertainty isn't a lack of ability that we'll technologically overcome. It's foundational. So that there's, in some sense, when it's in a precise location, it is fundamentally no longer in a precise motion. And that uncertainty principle means I can't precisely say a particle is exactly here, but it also means I can't say it's not. Okay. And so it led to this idea that what do I mean by a vacuum? Because I can't 100% precisely know. In fact, there's not really meaningful to say that there's zero particles here. And so what you can say, however, is you can say, well, maybe particles kind of froth around in this seething quantum sea of the vacuum. Maybe two particles come into existence and they're entangled in such a way that they cancel out each other's properties. So they have the properties of the vacuum. They don't destroy the kind of properties of the vacuum because they cancel out each other's spin, maybe each other's charge, maybe things like that. But they kind of froth around. They come, they go, they come, they go. And that's what we really think is the best that empty space can do in a quantum mechanical universe. Now, if you add an event horizon, which as we said is really fundamentally what a black hole is, that's the most important feature of a black hole. The event horizon, if the particles are created slightly on either side of that event horizon, now you have a real problem. Okay. Now the pair has been separated by this event horizon. Now they can both fall in, that's okay. But if one falls in and the other doesn't, it's stuck. It can't go back into the vacuum because now it has a charge or it has a spin or it has something that's no longer the property of that vacuum it came from. It needs its pair to disappear. Now it's stuck. It exists. It's like you've made it real. So in a sense, the black hole steals one of these virtual particles and forces the other to live. And if it'll escape, radiate out to infinity, and look like, to an observer far away, that the black hole has actually radiated a particle. And the particle did not emanate from inside. It came from the vacuum. It stole it from empty space, from the nothingness that is the black hole. Now, the reason why this is very tricky is because in the process, because of this separation on either side of the event horizon, the particle it absorbs, it has to do with the switching of space and time that we talked about, but the particle it absorbs, well, from the outside, you might say, oh, it had negative momentum, it was falling in. From the inside, you say, well, this is actually motion and time. This is energy. It has negative energy. And as it absorbs negative energy, its mass goes down. Black hole gets a little lighter. And as it continues to do this, the black hole really begins to evaporate. It does more than just radiate, it evaporates away. And it's intriguing because Hawking said, look, this is going to look thermal, meaning featureless. It's going to have no information in it. It's going to be the most informationless possibility you could possibly come up with when you're radiating particles. It's just going to look like a thermal distribution of particles, like a hot body.
Another idea to resolve the information paradox is firewalls. Proposed by Amiri, Marov, Polchinski, and Sully, AMPS.
Hmm.
This is a more drastic scenario arising from analyzing the entanglement requirements of Hawking radiation to preserve unitarity and avoid information loss. They argued that the entanglement structure requires the event horizon not to be the smooth, unremarkable place predicted by general relativity, the equivalence principle. Instead, it must be a highly energetic region, a quote, firewall that incinerates anything attempting to cross it. Okay, so yeah, that's a nice solution. Just destroy everything that crosses the. Do you find this at all a convincing resolution to the information?
I would say the firewall papers were fascinating and were very provocative and very important in making progress. I don't even think the authors of those papers thought firewalls were real. I think they were saying, look, we've been brushing too much under the rug. And if you look at the evaporation process, it's even worse than what you thought previously. It's so bad that I can't get away with some of these prior solutions that I thought I could get away with. There was a kind of duality idea or a complementarity idea that, oh, well, maybe one person thinks they fell in, one person thinks they never fell in, and that's okay. No big deal. They sort of exposed flaws in these kind of approaches, and it actually reinvigorated the campaign to find a solution. So it stopped it from stalling. I don't think anyone really believes that at the event horizon, you'll find a firewall. But it did lead to things like the entangled wormholes embroidering a black hole, which was born out of an attempt to address the concerns that AMPS raised. So it did lead to progress.
So for you, the resolution would.
I'm going back to the vacuum,
You go back
the empty space, the beautiful event horizon.
Yep.
I'll give up locality, meaning that I will allow things to be connected non-locally by a wormhole.
So that is the weirdest thing you're willing to allow for, which is arbitrary distance connection of particles through a wormhole. But quantum mechanics must be preserved.
I'll entertain pretty weird things, but I think that's the one that sounds promising. The implications are so dramatic because this is why you start to hear things like, wait a minute, if the event horizon only exists when it's sewn out of these quantum threads, does that mean that gravity is fundamentally quantum mechanics? Not that gravity and quantum mechanics get along and I have a quantum gravity theory and I now know how to quantize gravity. Actually, something much more dramatic. Gravity is just kind of emerging from this quantum description, that gravity isn't fundamental. And what is the only thing that we have when we go rock bottom, when we go deeper and deeper, smaller and smaller, is quantum mechanics. So all of this, like space-time looks nice and smooth and continuous, but if I look at the quantum realm, I'll see everything sewn together out of quantum threads. And that space-time is not a smooth continuum all the way down. Now, people already thought that, but they thought it kind of came in chunks of space-time. Instead, maybe it's just quantum mechanics all the way down.
Quantum threads, so these entangled particles connected by wormholes.
Yeah.
So that's how would you even visualize a black hole in that way? So it's all, it's all sort of from our perspective in terms of detecting things, the light going in,
Mhm.
it's all still the same. But when you zoom in a lot.
When you zoom in a lot to the quantum mechanical scale at which you're seeing the Hawking radiation, you would be noticing that there's some entanglement between the radiation that I could not explain before and the interior of the black hole. So it's now no longer a perfectly thermal spectrum with no features that only depends on the mass. It actually has a way to have an imprint of the information interior to the black hole in the particles that escape. And so now, in principle, I could sit there for a very long time, it might take longer than the age of the universe, and collect all the Hawking radiation and see that it actually had details in it that are going to explain to me what was interior to the black hole, so the information is no longer lost.
So information is not being destroyed, so in theory you should be able to get information.
Now I can't do that any more than I can recover the words on that piece of paper once it's been burnt, but that's a practical limitation, not a fundamental one. It's just too hard. But when I burn a piece of paper, technically the information is all there somewhere. It's in the smoke, it's in the currents, it's in the molecules, it's in the ink molecules, but in principle, if I took the age of the universe, I could probably reconstruct, I should be able to, in principle, reconstruct the piece of paper and all the words on it. And the temperature is going to only tell you about the mass, which you could tell from outside the black hole anyway. You know the mass of the black hole from the outside. So it's not telling you anything about the black hole. It's got no information about the black hole. Now you have a real problem. And when he first said it, a lot of people describe that not everyone understood how really naughty he was being. He did. But some people who love quantum mechanics were really annoyed. Okay, people like Lenny Susskind, Gerard 't Hooft, Nobel Prize winner, they were mad because it suggested something was fundamentally wrong with quantum mechanics, if it was right. And the reason why it says there's something fundamentally wrong with quantum mechanics is because quantum mechanics does not allow this. It does not allow quantum information to simply evaporate away and poof out of the universe and cease to exist. It's a violation of something called unitarity, but really the idea is it's the loss of quantum information that's intolerable. Quantum mechanics was built to preserve information. It's one of the sacred principles. As sacred as conservation of energy, in this example, more sacred, because you can violate conservation of energy with Heisenberg's uncertainty principle a little tiny bit. But so sacred that it created what became coined as the black hole wars, where people were saying, look, general relativity is wrong, something's wrong with our thinking about the event horizon, or quantum mechanics isn't what we think it is, but the two are not getting along anymore. And just to tell you how dramatic it is, so the temperature goes down with the mass of the black hole, heavier a black hole, the cooler it is. So we don't see black holes evaporate, they're way too big. But as they get smaller and smaller, they get hotter and hotter. So as the black hole nears the end of this cycle of evaporating away, it takes a very long time, much longer than the age of the universe, it will be as though the curtain, the event horizon's yanked up. Like it'll literally explode away, just boom. And the event horizon, in principle, would be yanked up. Everything's gone. All that information that went into the black hole, all that sacred quantum stuff, gone, poof. Okay, because it's not in the radiation, because the radiation has no information. And so it was an incredibly productive debate because in it are the signs of what will make gravity and quantum mechanics play nice together, some quantum theory of gravity. Whatever these clues are, and they're hard to assemble. If you want a quantum gravity theory, it has to correctly predict the temperature of a black hole, the entropy of a black hole. It has to have all of these correct features. The black hole is the place on which we can test quantum gravity.
But it still has not been resolved.
It has not been fully resolved.
I looked up all the different ideas for the resolution. So there's the information loss, which is what you referred to.
Right.
It's perhaps the simplest, yet most radical resolution, is that information is truly lost. This would mean quantum mechanics, as we currently understand it, specifically unitarity, is incomplete or incorrect under these extreme gravitational conditions.
I'm unhappy with that. I would not be happy with information loss. I love that it's telling us that there's this crisis, because I do think it's giving us the clues. And we have to take them seriously.
For you, the gut is like...
Unitarity is going to be preserved.
The quantum mechanics is
We have to come to the
strong.
rescue. As Lenny Susskind in his book Black Hole Wars says, his subtitle is My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics.
Quantum mechanics, I love it.
It's something to that effect.
So then from string theory, one of the resolutions is called fuzzballs. I love physicists so much. Originating from string theory, this proposal suggests that black holes aren't a singularity surrounded by empty space and an event horizon. Instead, they are horizonless, complex, tangled objects, aka fuzzballs, made of strings and brains roughly the size of the would-be event horizon.
Yeah.
There's no single point of infinite density and no
Yeah.
true horizon to cross.
In some sense, it says there's no interior to the black hole. Nothing ever crosses. So I gave you this very nice story that there's no drama. Sometimes that's how it's described at the event horizon, and you fall through and there's nothing there. This other idea says, well, hold on a second. If it's really strings, as I get close to this magnifying quality and the slowing time down near the event horizon, it is as though I put a magnifying glass on things, and now the strings aren't so microscopic. They kind of smear around, and then they get caught like a tangle around the event horizon, and they just actually never fall through. I don't think that either. But it was
Yeah.
interesting.
So it's just adding a very large number of extra complex.
Degrees of freedom.
Yeah,
There are no teeny tiny marbles to fall through.
but it's similar to what we already have with quantum mechanics. It's just giving a
But
deeper,
it's
more
really
complicated.
saying the interior's just not there ever. Nothing falls in, so the information gets out because it never went in the first place.
Oh, interesting. So there is a strong statement there.
There's a
Okay.
strong statement there, yeah.
Okay, so soft hair challenges the classical no hair theorem by suggesting that black holes do possess subtle quantum quote hair. This isn't classical hair like charge, but very low energy quantum excitations, soft gravitons or photons at the event horizon that can store information about what fell in.
Worth trying, but I also don't think that that's the case. So the no hair theorems are formal proofs that the black hole is this featureless, perfect fundamental particle that we talked about. That all you can ever tell about the black hole is its electrical charge, its mass, and its spin, and that it cannot possess other features. It has no hair, is one way of describing it. And that those are proven mathematical proofs in the context of general relativity. So the idea is, well, therefore I can know nothing about what goes into the black hole, so the information is lost. But if they could have hair, I could say that's my black hole, because it have features that I could distinguish, and it could encode the information that went in this way. And the event horizon isn't so serious, isn't such a stark demarcation between events inside and outside, and where I can't know what happened inside or outside. And I don't think that's the resolution either, but it was worth a try.
Okay, the pros and cons of that one. The pros, it works within the framework of quantum field theory in curved spacetime, potentially requiring less radical modifications than fuzzballs or information loss. Recent work by Hawking, Perry, Strominger revitalized this idea. The cons is that the precise mechanism by which information is encoded and transferred to the radiation is still debated and technically challenging to work out fully, and indeed, it needs to store a vast amount of information. Okay, another one, this is a weird one, boy, is ER equals EPR.
This is probably it, though.
Oh, boy. So ER equals EPR is Einstein-Rosen bridge equals Einstein-Podolsky-Rosen bridge, posits a deep connection between quantum entanglement and space-time geometry, specifically Einstein-Rosen bridge, commonly known as wormholes. It suggests that entangled particles are connected by a non-traversable wormhole, so tiny wormholes connected. Okay.
I can say that this is not a situation where we can follow the chalk. We can't start at the beginning and calculate to the end. So it's still a conjecture. I think it's very profound, though. I kind of imagine Juan Maldacena, who's part of this, with Lenny Susskind. They were kind of like, oh, it's like ER equals EPR. They couldn't even formulate it properly. It was like an intuition that they had kind of landed on and now are trying to formalize. But to take a step back, one way of thinking about ER equals EPR, you have to talk about holography first. And holography, both Juan Maldacena really formalized it, Lenny Susskind suggested it. The idea of a black hole hologram is that all of the information in the black hole, whatever it is, whatever, entropy as a measure of information, whatever the entropy of the black hole is, which is telling you how much information is hidden in there, how much information you don't have direct access to, in some sense, is completely encoded in the area of the black hole. Meaning, as the area grows, the entropy grows. It does not grow as the volume. This actually turns out to be really, really important. If I tried to pack a lot of information into a volume, more information than I could pack, let's say, on the surface of a black hole, I would simply make a black hole. And I would find out, oh, I can't have more information than I can fit on the surface. So Lenny coined this a hologram. People who take it very seriously say, well, again, maybe the interior of the black hole just doesn't exist. It's a holographic projection of this two-dimensional surface. In fact, maybe I should take it all the way and say, so are we. Mm-hmm. The whole universe is a holographic projection of a lower dimensional surface, right? And so people have struggled, nobody's really landed it, to find a universe version of it. Oh, maybe there's a boundary to the universe where all the information is encoded, and this entire three-dimensional reality that's so compelling and so convincing is actually just a holographic projection. Juan Maldacena did something absolutely brilliant. It's the most highly cited paper in the history of physics. It was published in the late 90s. It has a very opaque title that would not lead you to believe it's as revelatory as it is. But he was able to show that a universe like in a box with gravity in it, it's not the same universe we observe, doesn't matter. It's just a hypothetical called an anti de Sitter space. This universe in a box, it has gravity, it has black holes, it has everything gravity can do in it. On its boundary is a theory with no gravity, a universe that can be described with no gravity at all, so no black holes and no information loss problem. And they're equivalent. That the interior universe in a box is a holographic projection of this quantum mechanics on the boundary. Pure quantum mechanics, purely unitary, no loss of information. None of this stuff could possibly be true. There can't be loss of information if this dictionary really works, if the interior is a hologram, a projection of the boundary. I know that's a lot.
Yeah. So there's some mathematics there, there's physics, and then there's trying to conceive what that actually means practically for us.
Well, what it would mean for us is that information can't be lost even if we don't know how to show it in the description in which there are black holes. It means it can't possibly be lost because it's equivalent to this description with no gravity in it at all, no event horizons, no black holes, just quantum mechanics. So it really strongly suggested that quantum mechanics was going to win in this battle, but it didn't show exactly how it was going to win. So then comes ER equals EPR, a visual way to imagine what this means. So ER has to do with little wormholes. EPR, Einstein, Podolsky, Rosen, has to do with quantum entanglement. The idea was, well, maybe the stuff that's interior to the black hole is quantum entangled, like EPR, quantum entangled, with the Hawking radiation outside the black hole that's escaping. And that quantum entanglement is what allows you to extract the information, because it's not actually physically moving from the interior to the exterior. It's just subtle quantum entanglement. And in fact, I can kind of think of the entire black hole. If I look at it and it looks like a solid shadow cast on the sky, some region of space-time, if I look at it very closely, I will see, oh no, it's actually sewn from these quantum wormholes, like embroidered. And so when I get up close, it's almost as though the event horizon isn't the fundamental feature on the space-time. The fundamental feature is the quantum entanglement embroidering the event horizon.
The embroidering is just tiny wormholes. So the quantum entanglement is when two particles are connected at arbitrary distances.
And they're connected by a wormhole.
And in this case, they would be connected by a wormhole.
So the reason why that's helpful, it helps you connect the interior to the exterior without trying to pass through the event horizon.
The cons of this theory is highly conceptual and abstract. The exact mechanism for information retrieval via these non-traversable wormholes is not fully understood. Primarily explored in theoretical toy models. Whoa, Gemini going hard. Theoretical toy models like the anti de Sitter space-time, rather than realistic black holes.
True. We do what we can do in baby steps.
So another idea to resolve the information paradox is firewalls. Proposed by Amiri, Maroff, Polchinski, and Sully, AMPS. This is a more drastic scenario arising from analyzing the entanglement requirements of Hawking radiation to preserve unitarity and avoid information loss. They argued that the entanglement structure requires the event horizon not to be the smooth, unremarkable place predicted by general relativity, the equivalence principle. Instead, it must be a highly energetic region, a quote firewall that incinerates anything attempting to cross it. Okay, so yeah, that's a nice solution. Just destroy everything that crosses this. Do you find this at all a convincing resolution to the information?
I would say the firewall papers were fascinating and were very provocative and very important in making progress. I don't even think the authors of those papers thought firewalls were real. I think they were saying, look, we've been brushing too much under the rug. And if you look at the evaporation process, it's even worse than what you thought previously. It's so bad that I can't get away with some of these prior solutions that I thought I could get away with. There was a kind of duality idea or a complementarity idea that, oh, well, maybe one person thinks they fell in, one person thinks they never fell in, and that's okay. No big deal. They sort of exposed flaws in these kind of approaches, and it actually reinvigorated the campaign to find a solution. So it stopped it from stalling. I don't think anyone really believes that at the event horizon you'll find a firewall. But it did lead to things like the entangled wormholes embroidering a black hole, which was born out of an attempt to address the concerns that AMPS raised. So it did lead to progress.
So for you, the resolution would...
I'm going back to the vacuum,
you go back
the
to
empty
that.
space, the beautiful event horizon.
Yep.
I'll give up locality, meaning that I will allow things to be connected non-locally by a wormhole.
So that is the weirdest thing you're willing to allow for, which is arbitrary distance connection of particles through a wormhole. But quantum mechanics must be preserved.
I'll entertain pretty weird things, but I think that's the one that sounds promising. The implications are so dramatic because this is why you start to hear things like, wait a minute, if the event horizon only exists when it's sewn out of these quantum threads, does that mean that gravity is fundamentally quantum mechanics? Not that gravity and quantum mechanics get along and I have a quantum gravity theory and I now know how to quantize gravity. Actually, something much more dramatic. Gravity is just kind of emerging from this quantum description, that gravity isn't fundamental. And what is the only thing that we have when we go rock bottom, when we go deeper and deeper, smaller and smaller, is quantum mechanics. So all of this, like space-time looks nice and smooth and continuous, but if I look at the quantum realm, I'll see everything sewn together out of quantum threads. And that space-time is not a smooth continuum all the way down. Now, people already thought that, but they thought it kind of came in chunks of space-time. Instead, maybe it's just quantum mechanics all the way down.
Quantum threads, so these entangled particles connected by wormholes.
Yeah.
So that's how would you even visualize a black hole in that way? So it's all, it's all sort of from our perspective in terms of detecting things, the light going in,
Mm-hmm.
it's all still the same. But when you zoom in a lot...
When you zoom in a lot to the quantum mechanical scale at which you're seeing the Hawking radiation, you would be noticing that there's some entanglement between the radiation that I could not explain before and the interior of the black hole. So it's now no longer a perfectly thermal spectrum with no features that only depends on the mass. It actually has a way to have an imprint of the information interior to the black hole in the particles that escape. And so now, in principle, I could sit there for a very long time, it might take longer than the age of the universe, and collect all the Hawking radiation and see that it actually had details in it that are going to explain to me what was interior to the black hole, so the information is no longer lost.
So information is not being destroyed, so in theory you should be able to get information.
Now I can't do that any more than I can recover the words on that piece of paper once it's been burnt, but that's a practical limitation, not a fundamental one. It's just too hard. But when I burn a piece of paper, technically the information is all there somewhere. It's in the smoke, it's in the currents, it's in the molecules, it's in the ink molecules. But in principle, if I took the age of the universe, I could probably I should be able to, in principle, reconstruct the piece of paper and all the words on it.
I apologize for the romanticized question, but what idea in the space of neuroscience, in the space of the human brain, is to you the most beautiful, mysterious, surprising?
What had always fascinated me, even when I was a pretty young kid, I think, was the paradox that lies in the fact that the brain is so mysterious and so seems so distant, but at the same time, it's responsible for the the full transparency of everyday life. It's the brain is literally what makes everything obvious and familiar, and there's always one in the room with you.
Yeah.
I used to teach when I taught at Princeton. I used to teach a cognitive neuroscience course, and the very last thing I would say to the students was, you know, people often, when people think of scientific inspiration, the metaphor is often, well, look to the stars. You know, the stars will inspire you to wonder at the universe and you know, think about your place in it and how things work. And I'm all for looking at the stars, but I've always been much more inspired, and kind of my sense of wonder comes from not from the distant, mysterious stars, but from the extremely intimately close brain.
Yeah.
There's something just endlessly fascinating to me about that.
Just like you said, the one is close and yet distant in terms of our understanding of it. Are you also captivated by the fact that this very conversation is happening because two brains are communicating?
Yes. Exactly.
I guess what I mean is the subjective nature of the experience. If we can take a small tangent into the mystical of it, the consciousness, or when you're saying you're captivated by the idea of the brain, are you talking about specifically the mechanism of cognition, or are you also just, like, at least for me, it's almost like paralyzing the beauty and the mystery of the fact that it creates the entirety of the experience, not just the reasoning capability, but
Yes.
the experience.
Well, I definitely resonate with that latter thought, and I often find discussions of artificial intelligence to be disappointingly narrow. You know, speaking as someone who has always had an interest in art.
Right. I was just gonna go there because it sounds like somebody who has an interest in art.
Yeah, I mean, there are many layers to, you know, to full bore human experience, and in some ways it's not enough to say, oh well, don't worry, you know, we're talking about cognition, but we'll add emotion, you know.
Yeah.
There's an incredible scope to what humans go through in every moment, and yes, so that's part of what fascinates me, is that our brains are producing that, but at the same time it's so mysterious to us how. You know, like we literally, like, our brains are literally in our heads producing this experience,
Producing the experience.
and yet there's it's so mysterious to us, and the scientific challenge of getting at the actual explanation for that is so overwhelming. That's just, I don't know, that certain people have fixations on particular questions, and that's just always been mine.
Yeah, I would say the poetry of that is fascinating, and I'm really interested in natural language as well. And when you look at artificial intelligence community, it always saddens me how much, when you try to create a benchmark for the community to gather around, how much of the magic of language is lost when you create that benchmark. That there's something, we talk about experience, the music of the language, the wit, something that makes a rich experience, something that would be required to pass the spirit of the Turing test, is lost in these benchmarks. And I wonder how to get it back in, because it's very difficult. The moment you try to do like real good rigorous science, you lose some of that magic. When you try to study cognition in a rigorous scientific way, it feels like you're losing some of the magic. The seeing cognition in a mechanistic way that AI at this stage in our history look at.
I agree with you, but at the same time, one thing that I found really exciting about that first wave of deep learning models in cognition was there was the fact that the people who were building these models were focused on the richness and complexity of human cognition. So an early debate in cognitive science, which I sort of witnessed as a grad student, was about something that sounds very dry, which is the formation of the past tense. But there were these two camps. One said, well, the mind encodes certain rules, and it also has a list of exceptions, because of course, the rule is add ed, but that's not always what you do, so you have to have a list of exceptions. And then there were the connectionists who, evolved into the deep learning people, who said, well, if you look carefully at the data, if you actually look at corpora, like language corpora, it turns out to be very rich, because yes, there are most verbs that, and you just tack on ed, and then there are exceptions, but there are rules that, there's the exceptions aren't just random. There are certain clues to which verbs should be exceptional, and then there are also exceptions to the exceptions. And there was a word that was kind of deployed in order to capture this, which was quasi-regular. In other words, there are rules, but it's messy, and there's structure even among the exceptions, and it would be, you could try to write down this structure in some sort of closed form, but really the right way to understand how the brain is handling all this, and by the way, producing all of this, is to build a deep neural network and train it on this data and see how it ends up representing all of this richness. So the way that deep learning was deployed in cognitive psychology was the spirit of it. It was about that richness. And that's something that I always found very, very compelling, still do.
Where do you, in these possible explanations to the Fermi paradox, why haven't we contacted aliens, do you land on?
Well, I think the most straightforward explanation is that there aren't any. Now, there are many other explanations too, so you can't be dogmatic about things that are just sort of gut feel. But, one of my favorite Twilight Zone episodes, I don't know if you ever saw this one, where this alien civilization finally comes to planet Earth and gives us this book that they really want us to have and to hold, and it's in this foreign language you don't understand. The cryptographers, they desperately try to decipher it as humans are going to visit this other alien planet, and they're all sending back postcards how wonderful it is and so forth, and they finally decipher the title. It's To Serve Man, and everyone's so thrilled. Oh, they're here to serve us. It all makes sense. And then just as one of the final cryptographers is going onto the alien ship, his helper runs and says, I've deciphered the rest of the book. To Serve Man. It's a cookbook. So
Yeah.
So yeah, is that a possibility? Sure. And so could they be watching us and just sort of waiting for us to get to a mature enough level? I don't know. It strikes me. Well, I think it'd be better to have this conversation after the James Webb Telescope. I mean, I do think that if we look at the atmospheres of many planets, there's now an estimate now that there's on order of one planet per star on average. So we've long known that, the galaxy, hundreds of billions of stars, numbers of galaxies, hundreds of billions of galaxies. So we're talking about hundreds of billions of planets. Oh my, and if we start to survey some of these planets, and one after the other, we just sort of find no evidence for any of the biological markers. It could be, of course, maybe life takes a radically different form. It'd be hard to know that. But I think, that would at least give us some insight on the life question. But I just don't see how we get insight on the civilization or consciousness question without, the direct connection. And it strikes me that if consciousness is ubiquitous, let's say life is. I'm willing to grant that. If consciousness is also ubiquitous, then I don't understand why they haven't been here or why there hasn't been substitution, because presumably they should be much further ahead of us. How unlikely would it be that we're of all consciousness in the universe, we're the most advanced? That would be such a special place for human beings that it's hard for me to grant that as a likely possibility. Rather, I think we're kind of run of the mill And there are many who are far more advanced than us. And I don't think that they would expend the energy to hide themselves.
So,
I don't think they care enough.
And so I see that's actually what I believe, that there's a very large number of civilizations that are far more advanced than us. But my sense is that humans are exceptionally limited, both in our direct sensory capabilities and our physics, our tools of sensing. That just like with the string theory and the multiple dimensions, we're just not, like, it's like, I honestly believe there could be stuff in front of our nose that we're just not seeing. Because we're too dumb, too much hubris, and I mean it's a bunch of stuff, and too ignorant as to the fabric of reality. All of those things. We're young.
Yeah.
In terms of intelligence.
But I guess what I'd say is, like, I'm on board with all of that as a real possibility. But then it does strike me that we are sufficiently able to observe the unit. Look, we can look back to, a fraction of the duration from here to just a fraction is left that we are unable to see. So however young we are, we have been able to sort of pierce the universe, and it just strikes me that there would be some signature, but maybe that's coming. But look, having said that, I certainly note the fact that it's rare that I stoop down while walking in Manhattan and sort of dig up some ants in the bushes on the side of the street and talk to the ants, right? Because it's just not interesting to me. So if we're like the ants on the cosmological landscape, then yeah, I can imagine that the super advanced aliens would be like who would ever, but I feel like we're sufficiently advanced that there should be some signature of that, but maybe it's coming.
I think the deeper fundamental problem between us and the ants is that we don't have a common language. It's not the interest. It's that we don't even have a common language. And so the alien civilizations don't even know how to communicate. Like, we humans have convinced ourselves we're special because we developed a language. You talk about the importance of language to the intelligence, but it makes you wonder, like, how very niche is that club that tribe we've created of language and linguistic type of systems that are very specific to our particular kinds of brains, and we share ideas together. We're all super excited that we can understand the universe because we came up with some notation and math. I wonder if there's some totally other kinds of language that communicates on a different time scale with very different mechanisms in the space of information that just is not.
Sure.
Everything is lost in translation.
Yeah, and it could well be. Look, I mean, I think part of the reason I go toward the possibility of the soul intelligence is there's a certain kind of romantic appeal to looking out in the cosmos and it's just quiet and it's just eternal silence. There's something that appeals to me at an emotional level that way. But yeah, I mean, nobody knows, and it's certainly conceivable that there's just a radical mismatch between the kinds of things that we are able to observe and sensitive to versus the kinds of structures that permeate the universe in a manner that simply we're unable to detect.
Let me ask the Fermi paradox question. Let's say we live in this incredibly dark and beautiful world of just billions of planets with bacteria on it and very few intelligent civilizations, and yet there's a few out there. Why haven't we at scale seen them visit us? What's your sense? Is it because they don't exist? Is it because...
Well, don't exist in the right part of the universe at the right time. That's the simplest answer for it.
Is that the one you find the most compelling, or is there some other explanation?
I find that, it's not that I find it more compelling, it's that I find more probable, and I find all of them, I mean, there's a lot of hand-waving in this, we just don't know. So I'm trying to read out from what I know about life on Earth to what might happen somewhere else. And it gives, to my mind, a bit of a pessimistic view of bacteria everywhere and only occasional intelligent life. running forward, humans only once on Earth and nothing else that you would necessarily be any more excited about making contact with than you would be making contact with them on Earth. So I think the chances are pretty limited, and the chances of us surviving is pretty limited too. And the way we're going on at the moment, the likelihood of us not making ourselves extinct within the next few hundred years, possibly within the next 50 or 100 years, seems quite small. I hope we can do better than that. So maybe the only thing that will survive from humanity will be AI, and maybe AI, once it exists and once it's capable of effectively copying itself and cutting humans out of the loop, then maybe that will take over the universe.
I mean, there's a kind of inherent sadness to the way you described that, but isn't that also potentially beautiful, that that's the next step of life? I suppose, as from your perspective, as long as it carries the flame of consciousness somehow.
I think, yes, there can be some beauty to it being the next step of life, and I don't know if consciousness matters or not from that point of view, to be honest with you.
Yeah.
But there's some sadness, yes, probably, because I think it comes down to the selfishness that we were talking about earlier on. I am an individual with a desire not to be kind of displaced from life. I want to stay alive. I want to be here. So I suppose the threat that a lot of people would feel is that we will just be wiped out. So that we will be that there will be potential conflict between AI and humans, and that AI will win because it's a lot smarter.
Boy, would that be a sad state of affairs if consciousness is just an intermediate stage between bacteria and AI, right? And
I would see bacteria as being potentially a kind of primitive form of consciousness. Anyway.
Right. So maybe
the whole of life on Earth, to my mind,
it's conscious.
is capable of some form of feelings in response to the environment. That's not to say it's intelligent, though it's got its own algorithms for intelligence, but nothing comparable with us. I think it's beautiful what a sterile planet can come up with.
Yeah.
It's astonishing that it's come up with all of this stuff that we see around us, and that either we or whatever we produce is capable of destroying all of that. It is a sad thought, but it's also it's hugely pessimistic. I'd like to think that we're capable of giving rise to something which is at least as good, if not better, than us as AI.
Yeah, I have that same optimism, especially a thing that is able to propagate throughout the universe more efficiently than humans can, or extensions of humans, some merger with AI and humans, whether that comes from bioengineering of the human body to extend its life somehow, to carry that flame of consciousness and that personality and the beautiful tension that's within all of us, carry that through to multiple planets, to multiple solar systems, all out there in the universe. I mean, that's a beautiful vision. Whether AI can do that or bioengineered humans can, that's an exciting possibility, and especially meeting other alien civilizations in that same kind of way.
It's traditional to talk about the uncountability of the real numbers, so Cantor's big result was that the set of all real numbers is an uncountable set. So maybe if we're going to talk about countable sets, then I would suggest that we talk about Hilbert's Hotel, which really makes that idea perfectly clear.
Yeah, let's talk about the Hilbert's Hotel.
Hilbert's Hotel is a hotel with infinitely many rooms. Each room is a full floor suite. So there's floor 0. I always start with 0 because for me, the natural numbers start with 0, although that's maybe a point of contention for some mathematicians. The other mathematicians are wrong.
Like a bunch of Geoma programmers, so starting at 0 is a wonderful place to start.
Exactly. So there's floor 0, floor 1, floor 2, or room 0, 1, 2, 3, and so on, just like the natural numbers. So Hilbert's Hotel has a room for every natural number. And it's completely full. There's a person occupying room n for every n. But meanwhile, a new guest comes up to the desk and wants a room. Can I have a room, please? And the manager says, hang on a second, just give me a moment. And you see, when the other guests had checked in, they had to sign an agreement with the hotel that maybe there would be some changing of the rooms, during the stay. And so the manager sent a message up to all the current occupants and told every person, hey, can you move up one room, please? So the person in room 5 would move to room 6, and the person in room 6 would move to room 7, and so on, and everyone moved at the same time. And of course, we never want to be placing 2 different guests in the same room, and we want everyone to have their own private room. But when you move everyone up one room, then the bottom room, room 0, becomes available, of course, and so he can put the new guest in that room. So even when you have infinitely many things, then the new guest can be accommodated. And that's a way of showing how the particular infinity of the occupants of Hilbert's Hotel, it violates Euclid's principle. I mean, it exactly illustrates this idea, because adding one more element to a set didn't make it larger, because we can still have a one-to-one correspondence between the total new guests and the old guests by the room number, right?
So to just say one more time, the hotel is full,
The hotel is full.
and then you could still squeeze in one more, and that breaks the traditional notion of mathematics and breaks people's brains about when they try to think about infinity, I suppose. This is a property of infinity.
It's a property of infinity that sometimes when you add an element to a set, it doesn't get larger. That's what this example shows. But one can go on with Hilbert's Hotel, for example. I mean, maybe the next day, 20 people show up all at once. We can easily do the same trick again, just move everybody up 20 rooms. And then we would have 20 empty rooms at the bottom, and those new 20 guests could go in. But on the following weekend, a giant bus pulled up, Hilbert's bus. And Hilbert's bus has, of course, infinitely many seats. There's seat 0, seat 1, seat 2, seat 3, and so on. And so one wants to, all the people on the bus want to check into the hotel, but the hotel is completely full. And so what is the manager going to do? And when I talk about Hilbert's Hotel, when I teach Hilbert's Hotel in class, I always demand that the students provide, the explanation of how to do it. So maybe I'll ask you, can you tell me, what is your idea about how to fit them all in the hotel, everyone on the bus, and also the current occupants?
You separate the hotel into even and odd rooms, and you squeeze in the new Hilbert bus people into the odd rooms, and the previous occupants go into the even rooms.
That's exactly right. So, I mean, that's a very easy way to do it. If you just tell all the current guests to double their room number, so in room N, you move to room 2 times N. So they're all going to get their own private room, the new room, and it will always be an even number, because 2 times N is always an even number. And so all the odd rooms become empty that way, and now we can put the bus occupants into the odd numbered rooms.
And by doing so, you have now shoved in an infinity into another infinity.
That's right. So what it really shows, I mean, another way of thinking about it is that, well, we can define that a set is countable if it is equinumerous with a set of natural numbers. And a kind of easy way to understand what that's saying in terms of Hilbert's Hotel is that a set is countable if it fits into Hilbert's Hotel, because Hilbert's Hotel basically is the set of natural numbers in terms of the room numbers. So to be equinumerous with a set of natural numbers is just the same thing as to fit into Hilbert's Hotel. And so what we've shown is that if you have 2 countably infinite sets, then their union is also countably infinite. If you put them together and form a new set with all of the elements of either of them, then that union set is still only countably infinite. It didn't get bigger. And that's a remarkable property for a notion of infinity to have, I suppose. But if you thought that there was only one kind of infinity, then it wouldn't be surprising at all, because if you take 2 infinite sets and put them together, then it's still infinite. And so if there were only one kind of infinity, then it shouldn't be surprising that the union of 2 countable sets is countable. So there's another way to push this a bit harder, and that is when Hilbert's train arrives. And Hilbert's train has infinitely many train cars, and each train car has infinitely many seats. And so we have an infinity of infinities of the train passengers together with the current occupants of the hotel, and everybody on the train wants to check in to Hilbert's Hotel. So the manager can again, of course, send a message up to all the rooms telling every person to double their room number again. And so that will occupy all the even numbered rooms again, but free up again the odd numbered rooms. So somehow we want to put the train passengers into the odd numbered rooms. And so, well, every train passenger is on some car, let's say car C and seat S. So somehow we have to take these two coordinates, C comma S, the car number and the seat number, and produce from it an odd number in a one-to-one way. And that's actually not very difficult. In fact, one can just use, say, an easy way to do it is to just use the number 3 to the C times 5 to the S. 3 to the C, 3 to the car number. So 3 times 3 times 3, the number of the car. You multiply 3 by itself, the number of the train car, and then you multiply 5 by itself, the seat number times, and then you multiply those two numbers together. So 3 to the C times 5 to the S. That's always an odd number because the prime factorization has only 3s and 5s in it. There's no 2 there. So therefore it's definitely an odd number. And it's always different because of the uniqueness of prime factorization. So every number can be factored uniquely into prime. So if you have a number of that form, then you can just factor it, and that tells you the exponent on 3 and the exponent on 5. And so you know exactly which person it was, which car they came from, and which seat they came from.
And prime factorization is every single number can be decomposed into the atoms of mathematics, which is the prime numbers. You can multiply them together to achieve that number. That's prime factorization. You're showing 3 and 5 are both prime numbers, odd. So through this magical formula, you can deal with this train infinite number of cars, with each car having infinite number of seats.
Exactly right. We've proved that if you have countably many countable sets, then the union of those sets, putting all those sets together into one giant set, is still countable. Because the train cars are each countable, plus the current hotel is sort of like another train car, if you want to think about it that way. The current occupants of the hotel could, have the same number as any of the train cars. So putting countably many countable sets together to make one big union set is still countable. It's quite remarkable, I think. When I first learned this many, many years ago, I was completely shocked by it and transfixed by it. It was quite amazing to me that this notion of countable infinity could be closed under this process of infinitely many infinities adding up still to the very same infinity, which is a strong instance, a strong violation of Euclid's principle once again, right? So the new set that we built has many more elements than the old set, in the sense that there's additional elements, but it doesn't have many more elements in terms of its size, because it's still just a countable infinity and it fits into Hubert's Hotel.
It is incredibly hard just to allow the possibility that it's a mystery and not to feel the urge to get the answer. It is incredibly hard, but it's possible, and it is liberating as a recovering addict to knowledge. Let me say what you gain from it. For instance, I understand the value of paradoxes. I appreciate paradoxes more. And to use another philosopher, Søren Kierkegaard, the Danish philosopher, said, a thinker without paradox is like a lover without passion. A paltry mediocrity.
Ooh, that's a good line.
All right? So, and Niels Bohr said, in similar vein, the great Danish also. Something about something about Danes. I think it all started with Hamlet, He said, the opposite of a simple truth is a falsity. But the opposite of a great truth is another great truth. In other words, things are not black and white, they're not. And I would even venture to say the most interesting things in life are like that. They're the ones which are ambiguous. Is an electron a particle or a wave? It depends how you set up an experiment. It will reveal itself as this or that, depending on how you set up an experiment. This bottle if you project it down onto the table, you will see more or less a square. If you project it onto a wall, you will see a different shape. A naive question would be, is it this or that? Because we understand that it's neither. But both projections reveal something. They reveal different sides of it. A paradox is like that. It's only paradoxical if we are confined in a particular vision, if we are wedded to a particular point of view. It's a harbinger, if you will, of a possibility of seeing things in a more, as they are, as a more sophisticated than we thought before. You see,
That's such a difficult idea for science to grapple with. That, you know, I don't know how, there's so many ways to describe this, but you could say maybe that the subjective experience of the world from an observer is actually fundamental.
but we know that. Our best physical theories tell us that unambiguously. In quantum mechanics, actually, you know, Heisenberg, I think, captured it the best when he said, what we observe is not reality itself, but reality subjected to our method of questioning. When I talk about electrons, for instance, so that there is a very specific way in which this is realized. There is a so-called double slit experiment, right? So, for those who don't know, it's you have a screen and you have an emitter from which you kind of shoot electrons, and in between you put another screen which has two vertical slits parallel to each other. If we were shooting, you know, tennis balls, each ball would go through one slit or another and then hit the screen behind this or that slit. So you would have, and let's say they're colored, they're painted. So there will be sort of bumps or spots of paint behind this or that. But that's not what happens when we shoot electrons. We see an interference pattern, as if we were actually sending a wave, so that each electron, it seems like each electron goes through both slits at once, and then has the audacity to interfere with itself, where at some points, you know, two crests would amplify, and at some points the crest and the trough would cancel each other. Yet, so that suggests, okay, so the electron is a wave, not so fast, because if you put a detector behind one of the slits and you say, I'm going to capture you, I'm going to find out which slit you went through, the pattern will change, and it will look like they're particles. So that's a very concrete realization of the idea that depending on how we set up an experiment, we will see different results. And the problem is that our psyche, I feel, kind of lagging behind, in part because maybe our scientists are not doing such a great job. So I take responsibility for this, that why haven't I explained this properly, you know? I tried, you know, in a bunch of talks and so on, so now I'm talking about this again. Our psyche kind of is lagging behind. We're still, even though our science has progressed so much from the certainty and the determinism and all of that of the 19th century, our psyche is somehow still attached to those ideas. The ideas of causality, of this naive determinism, that the world is a bunch of billiard balls hitting each other, driven by some blind forces. You know, that's not at all like it is. And we've known this for about 100 years at least, you know?
And you call this self-imposed limitation.
It is a self-imposed limitation when we pretend that, for instance, that this naive ideas of 19th century physics are still valid, and then start applying them to our lives, and then also derive conclusions from it. And for instance, people say, there is no free will. Why? Oh, because the world is just a bunch of billiard balls. Where is the free will? But excuse me, didn't you get the memo that this has been debunked thoroughly by the so-called quantum mechanics, which is our best scientific theory? This is not some kind of bullshit or some kind of, you know, concoction of a madman. This is our scientific theory, which has been confirmed by experiment. So we should pay attention to that. So, but of course, it's not just self-imposed limitation. Unfortunately, in this case, there is a big issue of education. So a lot of people are not aware of it through no fault of their own, because they were never properly taught that. Because our system is broken, education system is broken, especially in math. And then so where do you get information? You get information from our scientists who actually write popular books and so on, which is a great great thing that they do. But a lot of scientists somehow, when it comes to explaining the laws of physics, they're doing a fantastic job talking about this phenomenon, for instance, double slit experiment and things like that. But then, interviewed by Science magazine about free will and so on, they revert back to 19th century physics as if those developments actually never happened. So to me, this is single most important sort of issue in our popular science. The idea that somehow there is this world out there, but it's has nothing to do with me. So I can revel in the intricacies of these particles and their interactions, but completely ignore what implications this has for my own relationship to the physical reality, to my own life, because it's kind of scary, I guess,
But also, what are the tools with which we can talk about the observer, the subjective view in reality? What are the tools with which we could rigorously talk about free will and consciousness? What are the tools of mathematics that allow that? I don't think we have those tools.
Because we haven't been taught properly. So actually tools are there. For instance, I think, here I have to say, my conviction is that everybody knows. In the heart of hearts, everybody knows that there is that. There is something ineffable. There is something mysterious. And in fact, somehow immediately I feel the impulse to quote somebody on this, because as if my own opinion doesn't count.
Yeah. There's a long dead expert that has
Even
said it.
Einstein said that, so how, see, look at me. I am supposedly like this smart, intelligent person. I am afraid to say it and own it myself. I have to find confirmation. I have to find an authority who agrees with me. And in fact, it's not so difficult to find, because Albert Einstein literally said the most important thing in life is the mysterious. Okay, he actually said that. There are some quotes which are attributed to him, which he never said, but this he did. I investigated, okay? So, but more importantly, how do you feel about it? I think that everybody knows. But, in other words, he also said, Einstein, imagination is more important than knowledge, okay? And he explained, for knowledge is always limited, whereas imagination embraces the entire world, giving birth to evolution. It is, strictly speaking, a real factor in scientific research, he says. And he says, I am enough of an artist to follow my intuition and imagination. That's Albert Einstein, again. So, and I feel the same way, to be honest. If I think about my own mathematical research, it's never linear. It's never like, give me more data, give me more data, give me more data, boom, the glass is full, and then I come up with a discovery. No, it's always felt as a jump, as a leap.
So can you speak to the uncountable infinities?
Yeah,
so what are the
absolutely.
integers and the real numbers, and what is the line that Cantor was able to find?
So maybe there's one more step I want to insert before doing that, which
Great.
is the rational numbers. So we did pairs of natural numbers, right? That's the train car basically. But maybe it's a little bit informative to think about the fractions, the set of fractions or rational numbers. Because a lot of people maybe have an expectation that maybe this is a bigger infinity because the rational numbers are densely ordered. Between any two fractions, you can find another fraction, right? The average of two fractions is another fraction. And so sometimes people, it seems to be a different character than the integers, which are discretely ordered, right? From any integer, there's a next one and a previous one and so on. But that's not true in the rational numbers. And yet, the rational numbers are also still only a countable infinity. And the way to see that is actually, it's just exactly the same as Hilbert's train again, because every fraction consists of two integers, the numerator and the denominator. And so if I tell you two natural numbers, then you know what fraction I'm talking about. I mean, plus the sign issue. I mean, if it's positive or negative. But if you just think about the positive fractions, then, you know, you have the numbers of the form p over q, where q is not 0. So you can still do 3 to the p times 5 to the q. The same idea works with the rational numbers. So this is still a countable set. And you might think, well, every set is going to be countable because there's only one infinity. I mean, if that's a kind of perspective maybe that you're adopting, but it's not true. And that's the profound achievement that Cantor made, is proving that the set of real numbers is not a countable infinity. It's a strictly larger infinity, and therefore there's more than one concept of infinity, more than one size of infinity.
So let's talk about the real numbers. What are the real numbers? Why did they break infinity, the countable infinity? Looking it up on Perplexity, real numbers include all the numbers that can be represented on the number line, encompassing both rational and irrational numbers. We've spoken about the rational numbers, and the rational numbers, by the way, are, by definition, the numbers that can be represented as a fraction of two integers.
That's right. So with the real numbers, we have the algebraic numbers. We have, of course, all the rational numbers. The integers and the rationals are all part of the real number system, but then also we have the algebraic numbers like the square root of 2 or the cube root of 5 and so on. Numbers that solve an algebraic equation over the integers, those are known as algebraic numbers. It was an open question for a long time whether that was all of the real numbers or whether there would exist numbers that are the transcendental numbers. The transcendental numbers are real numbers that are not algebraic.
And we won't even go to the surreal numbers, about which you have a wonderful blog post. We'll talk about that a little bit later.
Oh, great. So it was Louisville who first proved that there are transcendental numbers, and he exhibited a very specific number that's now known as the Louisville constant, which is a transcendental number. Cantor also famously proved that there are many, many transcendental numbers. In fact, it follows from his argument on the uncountability of the real numbers that there are uncountably many transcendental numbers. So most real numbers are transcendental.
And again, going to Perplexity, transcendental numbers are real or complex numbers that are not the root of any non-zero polynomial with integer or rational coefficients. This means they cannot be expressed as solutions to algebraic equations with integer coefficients, setting them apart from algebraic numbers.
That's right. So some of the famous transcendental numbers would include the number pi, you know, the 3.1415925 and so on. So that's a transcendental number. Also Euler's constant, the e, like e to the x, the exponential function.
So you could say that some of the sexiest numbers in mathematics are all transcendental
Absolutely,
numbers.
That's true. Yeah. Although, you know, I don't know, square root of 2 is pretty...
Square root, all right. So it depends. Let's not... Beauty can be found in all the different kinds of sets. But yeah.
And if you have a kind of simplicity attitude, then, you know, 0 and 1 are looking pretty good too. So, and they're definitely not.
Sorry to take that tangent, but what is your favorite number? Do you have one?
Oh, gosh. You know...
Is it 0?
Did you know there's a proof that every number is interesting? You can prove it because...
Yeah? What's that proof look like?
Yeah.
Well, how do you even begin?
I'm going to prove to you that every natural number is interesting.
Okay.
Yeah. I mean, 0 is interesting because, you know, it's the additive identity, right? That's pretty interesting. And 1 is the multiplicative identity. So when you multiply it by any other number, you just get that number back, right? And 2 is, you know, the first prime number. That's super interesting, right? And okay. So one can go on this way and give specific reasons, but I want to prove as a general principle that every number is interesting. And this is the proof. Suppose, toward contradiction, that there were some boring numbers. Okay. But if there was an uninteresting number,
yes,
then there would have to be a smallest uninteresting number.
Mm-hmm. Yes.
But that's a contradiction because the smallest uninteresting number is a super interesting property to have. So therefore, there cannot there cannot be any boring numbers.
I'm gonna have to try to find a hole in that proof because there's a lot of baked in the word interesting. But yeah, that's beautiful.
Right.
That doesn't say anything about the transcendental numbers, about the real numbers. You
That's
just proved
right.
for natural numbers.
Yeah. Okay, so should we get back to Cantor's argument? Or?
Sure.
Okay.
You've masterfully avoided the question. You basically said, "I love all numbers."
Yeah,
So
basically. Yeah,
okay,
that's
all right.
what my
Back to
intention.
Cantor's argument. Let's go.
Okay, so Cantor wants to prove that the infinity of the real numbers is different and strictly larger than the infinity of the natural numbers. So the natural numbers are the numbers that start with 0 and add 1 successively, so 0, 1, 2, 3, and so on. And the real numbers, as we said, are the numbers that come from the number line, including all the integers and the rationals and the algebraic numbers and the transcendental numbers and all of those numbers all together. Now, obviously, since the natural numbers are included in the real numbers, we know that the real numbers are at least as large as the natural numbers. And so the claim that we want to prove is that it's strictly larger. So suppose that it wasn't strictly larger. So then they would have the same size. But to have the same size, remember, means, by definition, that there's a one-to-one correspondence between them. So we suppose that the real numbers can be put into one-to-one correspondence with the natural numbers. So therefore, for every natural number n, we have a real number, let's call it r sub n. R sub n is the nth real number on the list. Basically, our assumption allows us to think of the real numbers as having been placed on a list, r1, r2, and so on. Okay, and now I'm going to define the number z, and it's going to be, the integer part is going to be a 0, and then I'm going to put a decimal place, and then I'm going to start specifying the digits of this number z. d1, d2, d3, and so on. What I'm going to make sure is that the nth digit after the decimal point of z is different from the nth digit of the nth number on the list. Okay, so to specify the nth digit of z, I go to the nth number on the list, r sub n, and I look at its nth digit after the decimal point. And whatever that digit is, I make sure that my digit is different from it. Okay, and then I want to do something a little bit more, and that is I'm going to make it different in a way that I'm never using the digits 0 or 9. I'm just always using the other digits and not 0 or 9. There's a certain technical reason to do that. But the main thing is that I make the digits of z different in the nth place from the nth digit of the nth number. If you had drawn out the numbers on the original list, R1, R2, R3, and so on, and you made it, and they were each filling a whole row, and you thought about the nth digit of the nth number, it would form a kind of diagonal going down and to the right. And for that reason, this argument is called the diagonal argument, because we're looking at the nth digit of the nth number, and those exist on a kind of diagonal going down. And we've made our number z so that the nth digit of z is different from the nth digit of the nth number. But now it follows that z is not on the list, because z is different from r1, because, well, the first digit after the decimal point of z is different from the first digit of r1 after the decimal point. That's exactly how we built it. And the second digit of z is different from the second digit of r2, and so on. The nth digit of z is different from the nth digit of r sub n for every n. So therefore, z is not equal to any of these numbers, r sub n. But that's a contradiction, because we had assumed that we had every real number on the list, but yet here is a real number z that's not on the list. Okay? And so that's the main contradiction.
And so it's a kind of proof by construction.
Exactly. So given a list of numbers, Cantor's proving that it's interesting that you say that, actually, because there's a kind of philosophical controversy that occurs as in connection with this observation about whether Cantor's construction is constructive or not. Given a list of numbers, Cantor gives us a specific means of constructing a real number that's not on the list, is a way of thinking about it. There's this one aspect which I alluded to earlier, but some real numbers have more than one decimal representation, and it causes this slight problem in the argument. For example, the number 1. You can write it as 1.0000 forever, but you can also write it as 0.999 forever. Those are two different decimal representations of exactly the same number.
And you beautifully got rid of the zeros and the nines, therefore we don't need to even consider that,
Yes.
and the proof still works.
Exactly. Because the only kind of case where that phenomenon occurs is when the number is eventually 0 or eventually 9. And so since our number z never had any zeros or nines in it, it wasn't one of those numbers. And so actually in those cases, we didn't need to do anything special to diagonalize. Just the mere fact that our number has a unique representation already means that it's not equal to those numbers. So maybe it was controversial in Cantor's day more than 100 years ago, but I think it's most commonly looked at today as, one of the initial main results in set theory, and it's profound and amazing and insightful and the beginning point of so many later arguments. And this diagonalization idea has proved to be an extremely fruitful proof method, and almost every major result in mathematical logic is using in an abstract way the idea of diagonalization. It was really the start of so many other observations that were made, including Russell's paradox and the halting problem and the recursion theorem, and so many other principles are using diagonalization at their core. So
there's always going to be the paradox of another meta level you could build on the meta level, right? So like if you assume this is your universe and you're the observer outside of it, you have some meta description of that universe, but then you need a meta description of you describing that universe, right? So, this is one of the biggest challenges that we face, being observers inside our universe, and also, why the paradoxes and the foundations of mathematics and any place that we try to have observers in the system or a system describing itself show up. But I think it is possible to build a physics that builds in those things intrinsically without having them be paradoxical or have holes in the descriptions. And so one place I think about this quite a lot, which I think can give you sort of a more concrete example, is the nature of like what we call fundamental. So we typically define fundamental right now in terms of the smallest indivisible units of matter. So again, you have to have a definition of what you think material is and matter is. But right now, what's fundamental are elementary particles. And we think they're fundamental because we can't break them apart further. And obviously we have theories like string theory that, if they're right, would replace the current description of what's the most fundamental thing in our universe by replacing it with something smaller. But we can't get to those theories because we're technologically limited. And so if you look at this from a historical perspective and you think about explanations changing as physical systems like us learn more about the reality in which they live, we once considered atoms to be the most fundamental thing. And it literally comes from the word indivisible. And then we realized atoms had substructure because we built better technology, which allowed us to quote unquote see the world better and resolve smaller features of it. And then we built even better technology, which allowed us to see even smaller structure and get down to the standard model particles. And we think that there's might be structure below that, but we can't get there yet with our technology. So what's fundamental, the way we talk about it in current physics, is not actually fundamental. It's the boundaries of what we can observe in our universe, what we can see with our technology. And so if you want to build a theory that's about us and about what's inside the universe that we can observe, not what's at the boundary of it, you need to talk about objects that are in the universe that you can actually break apart to smaller things. So I think the things that are fundamental are actually the constructed objects. They're the ones that really exist and you really understand their properties because you know how the universe constructed them, because you can actually take them apart. You can understand the intrinsic laws that built them. But the things at the boundary are just at the boundary. They're evolving with us, and we'll learn more about that structure as we go along. But really, if we want to talk about what's fundamental inside our universe, we have to talk about all these things that are traditionally considered emergent, but really just structures in time that have causal histories that constructed them and are really actually what our universe is about.
So we should focus on the construction methodology as the fundamental thing. But do you think there's a bottom to the smallest possible thing that makes up the universe?
I don't see one.
And it'll take way too long. It'll take longer to find that than it will to understand the mechanism that created life.
I think so, yeah. I think for me, the frontier in modern physics, where the new physics lies, is not in high energy particle physics. It's not in quantum gravity. It's not in any of these sort of traditionally sold, this is going to be the newest, deepest insight we have into the nature of reality. It is going to be in studying the problems of life and intelligence and the things that are sort of also our current existential crises as a civilization or a culture that's going through an existential trauma of inventing technologies that we don't understand right now.
The existential trauma and the terror we feel that technology might somehow destroy us meaning intelligent living organisms.
Right.
And yet we don't understand what that even means.
Well, humans have always been afraid of our technologies, though, right? So it's kind of a fascinating thing that every time we invent something we don't understand, it takes us a little while to catch up with it.
I think also in part humans kind of love being afraid.
Yeah, we love being traumatized.
It's weird.
We want to learn more, and then when we learn more, it traumatizes us. I never thought about it this before, but I think this is one of the reasons I love what I do is because it traumatizes me all the time. That stuff is really bad. But what I mean is, I love the shock of, realizing that, coming to understand something in a way that you never understood it before. I think it seems to me when I see a lot of the ways other people react to new ideas that they don't feel that way intrinsically. But for me, that's why I do what I do. I love that feeling. But
you're also working on a topic where it's fundamentally ego destroying because you're talking about life. It's humbling to think that the individual human is not special.
Yeah.
And you're very viscerally exploring that.
Yeah. I'm trying to embody that because I think you have to live the physics to understand it. But there's a great quote about Einstein. I don't know if this is true or not, that he once said that he could feel a light beam in his belly. And I think, but I think you got to think about it though, right? If you're a really deep thinker and you're really thinking about reality that deeply, and you are part of the reality that you're trying to describe, you feel it, you really feel it.
That's what I was saying about you're always walking along the cliff. If you fall off, you're falling into madness.
Yes, it's a constant descent into madness.
The fascinating thing about physicists and madness is that you don't know if you've fallen off the cliff.
Yeah, you don't know.
That's the cool thing about
I rely
madness.
on other people to tell me. Actually, this is very funny because I have these conversations with my students often. They're worried about going crazy. And I get to reassure them that one of the reasons they'll stay sane is by trying to work on concrete problems.
Going crazy or waking up? I don't know which one it is.
Yeah.
You mentioned to me offline, we were talking about Russell's paradox, and that there's another kind of anthropomorphizable proof of uncountability. I was wondering if you can lay that out.
Oh yeah, sure, absolutely.
Both Russell's paradox and the proof.
Right. So we talked about Cantor's proof that the set of real numbers is an uncountable infinity. It's a strictly larger infinity than the natural numbers. But Cantor actually proved a much more general fact, namely that for any set whatsoever, the power set of that set is a strictly larger set. So the power set is the set containing all the subsets of the original set. So if you have a set and you look at the collection of all of its subsets, then Cantor proved that this is a bigger set. They're not equinumerous. Of course, there's always at least as many subsets as elements, because for any element you can make the singleton subset that has only that guy as a member, right? So there's always at least as many subsets as elements. But the question is whether it's strictly more or not. And so Cantor reasoned like this. It's very simple. It's a kind of distilling the abstract diagonalization idea without encumbered by the complexity of the real numbers. So we have a set X, and we're looking at all of its subsets. That's the power set of X. Suppose that X and the power set of X have the same size. Suppose towards contradiction, they have the same size. So that means we can associate to every individual of X a subset. And so now let me define another set. I'm going to define it. Let's call it D. And D is the subset of X that contains all the individuals that are not in their set. Every individual was associated with a subset of X, and I'm looking at the individuals that are not in their set. Maybe nobody's like that. Maybe there's no element of X that's like that. Or maybe they're all like that. Or maybe some of them are and some of them aren't. It doesn't really matter for the argument. I defined a subset D consisting of the individuals that are not in the set that's attached to them. But that's a perfectly good subset. And so because of the equinumerosity, it would have to be attached to a particular individual, But let's call that person, it should be a name starting with D, so Diana. And now we ask, is Diana an element of D or not? But if Diana is an element of D, then she is in her set. So she shouldn't be, because the set D was the set of individuals that are not in their set. So if Diana is in D, then she shouldn't be. But if she isn't in D, then she wouldn't be in her set, and so she should be in D. That's a contradiction. So therefore, the number of subsets is always greater than the number of elements for any set. And the anthropomorphizing idea is the following. I like to talk about it this way. For any collection of people, you can form more committees from them than there are people. Even if you have infinitely many people. Suppose you have an infinite set of people. And what's a committee? Well, a committee is just a list of who's on the committee, basically, the members of the committee. So there's all the 2-person committees, and there's all the 1-person committees, and there's the universal, the worst committee, the one that everyone is on. Okay, the best committee is the empty committee with no members and never meets and so on. Or is the empty committee meeting all the time? I'm not sure.
That's a profound question. And does a committee with just one member meet also?
Maybe it's always in session. I don't know. Okay.
Yeah.
So the claim is that there's more committees than people. Okay, suppose not. Well, then we could make an association between the people and the committees. So we would have a kind of, every committee could be named after a person in a one-to-one way. And I'm not saying that the person is on the committee that's named after them or not on it, whatever. Maybe sometimes that happens, sometimes it doesn't. I don't know. It doesn't matter. But let's form what I call Committee D, which consists of all the people that are not on the committee that's named after them. Okay, maybe that's everyone. Maybe it's no one. Maybe it's half the people. It doesn't matter. That's a committee. It's a set of people. And so it has to be named after someone. Let's call that person Daniela. So now we ask, is Daniela on the committee that's named after her? Well, if she is, then she shouldn't be, because it was the committee of people who aren't on their own committee. And if she isn't, then she should be. So again, it's a contradiction. So when I was teaching in Oxford, one of my students came up with the following different anthropomorphization of Cantor's argument. Let's consider all possible fruit salads. We have a given collection of fruits, apples and oranges and grapes, whatever. And a fruit salad consists of some collection of those fruits. So there's the banana, pear, grape salad, and so on. There's a lot of different kinds of salad. Every set of fruits makes a salad, a fruit salad. And we want to prove that for any collection of fruits, even if there are infinitely many different kinds of fruit, for any collection of fruits, there are more possible fruit salads than there are fruits. So if not, then you can put a one-to-one correspondence between the fruits and the fruit salads. So you could name every fruit salad after a fruit. That fruit might not be in that cell, it doesn't matter. It's a naming, a one-to-one correspondence. And then, of course, we form the diagonal salad, which consists of all the fruits that are not in the salad that's named after them. And that's a perfectly good salad. It might be the kind of diet salad if it was the empty salad, or it might be the universal salad, which had all fruits in it, if all the fruits are in it. Or it might have just some and not all. So that diagonal salad would have to be named after some fruit. So let's suppose it's named after durian, meaning that it was associated with durian in the one-to-one correspondence. And then we ask, well, is durian in the salad that it's named after? And if it is, then it shouldn't be. And if it isn't, then it should be. And so it's again the same contradiction. So all of those arguments are just the same as Cantor's proof that the power set of any set is bigger than the set. And this is exactly the same logic that comes up in Russell's paradox, because Russell is arguing that the class of all sets can't be a set, because if it were, then we could form the set of all sets that are not elements of themselves. So basically, what Russell is proving is that there are more collections of sets than elements, because we can form the diagonal class, the class of all sets that are not elements of themselves. If that were a set, then it would be an element of itself if and only if it was not an element of itself. It's exactly the same logic in all four of those arguments. So there can't be a class of all sets, because if there were, then there would have to be a class of all sets that aren't elements of themselves. But that set would be an element of itself if and only if it's not an element of itself, which is a contradiction. So this is the essence of the Russell paradox. I don't call it the Russell paradox. Actually, when I teach it, I call it Russell's theorem. There's no universal set. And it's not really confusing anymore. At the time, it was very confusing. But now we've absorbed this nature of set theory into our fundamental understanding of how sets are, and it's not confusing anymore. I mean, the history is fascinating, though, of the Russell paradox, because before that time, Frege was working on his monumental work, implementing the philosophy of logicism, which is the attempt to reduce all of mathematics to logic. So Frege wanted to give an account of all of mathematics in terms of logical notions. And he was writing this monumental work and had formulated his basic principles. And those principles happened to imply that for any property whatsoever, you could form the set of objects with that property. This is known as the general comprehension principle. And he was appealing to the principles that support that axiom throughout his work. I mean, it wasn't just an incidental thing. He was really using this principle. And Russell wrote him a letter when he observed the work in progress, that there was this problem, because if you accept the principle that for any property whatsoever you can make the set of objects with that property, then you could form the set of all sets that are not members of themselves. That's just an instance of the general comprehension principle. But the set of all sets that aren't elements of themselves can't be a set, because if it were, then it would be an element of itself if and only if it's not a member of itself, and that's a contradiction. And so Russell wrote this letter to Frege, and it was just at the moment when Frege was finishing his work. It was already at the publishers and, in press, basically. But it's completely devastating. I mean, it must have been such a horrible situation for Frege to be placed in, because he's finished this monumental work, years of his life dedicated to this, and Russell finds this basically one-line proof of a contradiction in the fundamental principles of the thesis that completely destroys the whole system. And Frege had put in the appendix of his work a response to Russell's letter in which he explained what happened, and he wrote very gracefully, "Hardly anything more unwelcome can befall a scientific writer than to have one of the foundations of his edifice shaken after the work is finished. This is the position into which I was put by a letter from Mr. Bertrand Russell as the printing of this volume was nearing completion." And then he goes on to explain the matter concerns his basic law 5 and so on. And
it's heartbreaking. I mean, there's nothing more traumatic to a person who dreams of constructing mathematics all from logic to get a very clean, simple contradiction. I mean, that's just...
you devote your life to this work, and then it's shown to be contradictory, and that must have been heartbreaking.
What do you think about the Frege project, the philosophy of logic, the dream of the power of logic to construct the mathematical universe?
So, of course, the the project of logicism did not die with Frege, and it was continued. And there's a whole movement, the neo-logicists and so on, in contemporary times even. But my view of the matter is that really we should view the main goals of logicism are basically completely fulfilled in the rise of set theoretic foundationalism. I mean, when you view ZFC as the foundation of mathematics, and in my view, the principles of ZFC are fundamentally logical in character, including the axiom of choice, as I mentioned, as a principle of logic. This is a highly disputed point of view, though, because a lot of people take even the axiom of infinity as mathematical, inherently mathematical, and not logical, and so on. But I think if you adopt the view that the principles of ZFC have to do with the principles of abstract, set formation, which is fundamentally logical in character, then it's complete success for logicism. So the fact that set theory is able to serve as a foundation means that mathematics can be founded on logic.
Let me ask you another trippy out there question. Again, perhaps unanswerable from a physics perspective, but do you wonder about alien civilizations? Do you wonder about other intelligent beings out there making up their own math and physics, trying to figure out the world? Do you think they're out there?
It is hard to understand why there would, given that there's so many planets, and of course there's Drake's formula, and we don't exactly know but I mean, I think Fermi's paradox that, is a real paradox, and I think there probably are, and I think it's very exciting that we might find some. It's a logical possibility that we could learn about it.
I mean, to me, it's super interesting to think about aliens from a perspective of physics, because any intelligent civilization is going to be contending with the ideas, just trying to understand the world around it. So I think that the universe is filled with alien civilizations. So they all have their physicists, right? They're all trying to understand the world around them. And it's just interesting to me to imagine all these different perspectives, all these different Einsteins.
Yeah.
Like trying to make sense of
Though they might be more different than we think.
They
might be different in a way that we haven't even thought of.
Like smarter or different?
Just different, something that we're not even able to describe now. We just haven't thought of it,
Yeah, this is the really frustrating thing when we think from me as an AI person, you start to think about what is intelligence, what is consciousness, and you start to sometimes, again, evening thoughts is how little we understand, how narrow our thinking is about these concepts.
Yeah.
That it could be intelligence, could be something, could be intelligent and be very different, intelligent in a very different way that we won't be able to detect because we're not keeping an open enough mind. And that's kind of sad, because to me there's also just a strong possibility that aliens or something like alien intelligence or some fascinating, beautiful physical phenomena are all around us, and we're too dumb to see it for now. We're too closed-minded to see it. There's something we're just deeply missing, whether it's like fundamental limitations of our cognitive abilities, or just because our tools are too primitive right now, or like the way it's like you said, like the ideas seem trivial once you figured it all out, looking back.
Yeah.
But that kind of makes me sad, because there could be so much beauty in the world we're not seeing because we're too dumb.
There surely is.
And that's, I guess, the process of science and physics, is to keep exploring, to keep exploring, to find the thing that will, in a century, seem obvious.
Well, something we know for sure. I mean, the brain we don't really understand, and that's got to be some fabulously beautiful story.
I'm hoping some of that story will be written through the process of trying to build a brain, so the process of engineering intelligence, not just the neuroscience perspective of just looking at the brain, but trying to create it. But yeah, that story hasn't been written almost at all. Or just the early days of figuring that one out. But see, like you said, that math is discovered, so aliens should at least have the same math as us, right?
I think so.
Maybe different symbols.
Oh, well, they might have discovered it differently. And they might have had a different idea of what a proof is.
Sure. Yeah, we're very like black and white with the proof thing.
Yeah.
Maybe they're looser.
Right. Well, so you can know something is true. First of all, you never know something is true with 100% uncertainty. I mean, you might have had a blackout at some, it's never 100%, right? You might have had a momentary lapse of consciousness as the key step in the proof, and nobody read it, and whatever. Okay, so you never know for sure. But you have a preponderance of evidence, which makes it. And preponderance of evidence is not accepted very much in mathematics, and that was sort of how, the famous Ramanujan work. He worked. He had formulas which he guessed at, and then he gathered a preponderance of evidence that he was sure they were true, and so there might be, or something completely different. They might function in a very different way.
Where does freedom come from if we don't have any kind of physics-based free will?
Yeah, and so the idea follows naturally from all that we've been talking about. Let's make the assumption that all there is in the physical universe is stuff governed by laws. We may not have those laws, may not know what the fundamental stuff is yet, but everything we know in science points in the direction that it's physical stuff governed by universal laws. And that being the case, or that being the assumption, then you come to a particular collection of those ingredients called a human being, and that human being has particles that are fully governed by physical law. And when you then recognize that every thought that we have, every action that we undertake is just the motion of particles. When I'm thinking thoughts right now, of course, at this level of description, it is the motion of particles cascading down various neurons inside of my head and so on. And every single one of those motions, collectively and individually, is fully governed by these laws that we perhaps don't have yet, but we imagine one day we will. That leaves no opportunity for any kind of freedom to break free from the constraint of physical law. And that is the end of the story. So the traditional intuitive notion of free will, that we're the ultimate authors of our actions, that we're where the buck stops, that there is no antecedent that is the cause for our deciding to go left or right, choose vanilla or chocolate, live or die, that intuitive sensation does not have a basis in our understanding of the physical world. So that's the end of the free will of the traditional sort. But then your question is, what about this other kind of freedom I talk about? And the other kind of freedom, if you focus on it intently, I think is actually the true version of freedom that we feel. And that freedom is this. You look at inanimate objects in the world, rocks, bottles of water, whatever, they have a very limited behavioral repertoire. Why? Their internal organization is too coarse for them to do very much, right? You try to have a conversation with a glass of water, you send sound waves, it doesn't do much. It may vibrate a little bit, but the repertoire of responses are incredibly limited. The difference between us and a rock or a bottle of water is that our inner organization, by virtue of eons of evolution by natural selection, is so refined, so spectacularly ordered, that we have a huge repertoire of behaviors that are finely attuned to stimuli from the external world. You ask me a question, that's a stimulus, and all of a sudden, these particle processes go into action, and this is the result, this answer that I'm giving you. So the freedom that we have is not from the control of physical law. The freedom that we have is from the constrained behavior that has long since governed inanimate objects. We are liberated from the limited behavioral repertoire of rocks and bottles of water to have this broad spectrum of responses. Do we pick them? We do not. Do we freely choose them? We do not. But yet we have them, and we can marvel at those behaviors, and that's the freedom that we have.
The complexity and the breadth of that repertoire is where the freedom
Yes.
emerges. Is it nevertheless surprising to you that we have not destroyed ourselves with nuclear weapons? So the mutually assured destruction that we've had for many decades, from somebody who studies violence, how does that make sense to you?
Well, I mean, I'm surprised only in the sense that the fact that we have not had an accident yet has been quite remarkable. Because all the accounts are that we've come very close to having very serious accidents where people on either side have misread intentions or apparent launches and so on. So yes, I think it is remarkable. There's a nasty generalization that can be made that the longer that powerful states go without having wars, then the worse the war is afterwards. You can sort of see that kind of makes sense, because basically what's happening with these tribal groups that the nations are at the moment is that after a big war like the Second World War, they establish new kinds of dominance relationships. And then during the periods of peace, what happens is that the de facto dominance relationships change, because some nations become poorer, some become richer, some become more militarily powerful, and so on. Generally, economy and military go hand in hand. So, right now, China emerged from the war as a relatively low status state and is now high status. So if these were chimpanzees, what would happen is that you would predict a conflict, because you need to have a readjustment of the formal dominance relationships to recognize the new, in practice, dominance relationships recognized by the economy and the military. So the longer that you have of a period of peace following a war, then the more these tensions of unresolved, changed dominance relationships build up. And the longer they take to occur, then the more challenging are going to be the conflicts.
That's a terrifying view, because we've been out of conflict for quite a bit.
That's
So
right.
Maybe it's building up.
So it's a scary view. But on the other hand, things have changed hugely with the advent of nuclear weapons, because at least that conforms to this psychology that is very clear in other animals, which is you don't want to get into a fight if you are going to get hurt. So that's the whole principle of MAD, mutually assured destruction. And it's doubtless been why powerful nations like America and Russia have not used their nuclear weapons since 1945. So if we can overcome the problem of accidental launches, then maybe the fact of MAD does fit into human psychology in a way that means that we really will resolve our tensions without using them. But we haven't yet really faced that challenge. The Soviet Union collapsed because of the poor economy, but with China, desperate to take back Taiwan, and America shifting its focus on the Pacific, the potential for something going wrong is clearly very high.
So what's the hopeful case that you can make for a long-term surviving and thriving human civilization, given all the dangers that we face?
Well, I can't really exactly make one. I would just say that we're talking about the dangers. Obviously, the dangers are there.
Yeah.
But what I would sort of think about is the notion that surprises come from all sorts of different directions. And you work in robotics, and I can well imagine that there will be advances in robotics that in some way I can't even conceive will somehow undermine the motivation for conflict. Something about, by the time chips have been planted in human brains and we're all instantly sharing information in a way that we never did before, will this change the nature of human existence in such a way that these conflicts get resolved?
So remove the conflicts, but keep some of the magic, the beauty of what it means to be human. So like still be able to enjoy life, the richness of life, the full complexity of life. Because you can remove conflict by giving everybody a pill, and then they go to sleep, right? You still want life to be amazing, exciting, interesting. And so that's where you have to find the balance.
Well, it's all science fiction stuff, and so how it's going to work out, totally unclear. I don't see any worry about the magic of life disappearing. I mean, first of all, you somehow get rid of males. I think you really need to get rid of males, because males are the source of a major problem, which is the lust for power and the resulting conflict.
But you don't think the males are also a source of beauty and creation?
No. I mean, I don't have anything against males as individuals and that sort of thing, and males have clearly done a lot. I mean, they've been incredibly exploratory and creative, and what they've done in art and music has been wonderful, and that sort of thing. On the other hand, I'm not sure there's anything particularly special, and I think that probably females could do the same thing just as well when given the chance.
Yes, including the dark stuff. I mean, a part of me is not understanding so there is evolutionary distinction between men and women, but I tend to believe both men and women, if you look out into the future, can be destructive, can be evil, can be greedy, can be corrupted by power. So if you move males from the picture, which are historically connected to this evolution that we've been talking about, that women are going to fill that role quite nicely. And then it'll be just the same kind of process, not the same, but it'll be new and interesting. There's a sense that the will to power, craving power, committing violence is somehow coupled with all of the things that are beautiful about life. That if you remove conflict completely, if you remove all of the evil in the world, it seems like you're not going to have a stable place for the beauty, for the goodness. Like there's always has to be a dragon to fight for the way, if you look at human history. Now you can say, the reason I'm nervous about a sort of utopia where everything is great is every time you look through human history when utopia has been chased, you run into a lot of trouble where again sneaks into this evil, this craving for power. Now you could say that's a male problem, but I just think it's a human problem, and it's not even a human problem, it's a chimp problem too. It's life on Earth problem, intelligent life on Earth problem. So like it's better to not necessarily get rid of the sources of the darkest sides of human nature, but more create mechanisms that the kindness, the goodness, as the goodness paradox, your book, that is incentivized and encouraged, empowered.
Well, look, I don't think it would be utopia if you got rid of the males.
Right.
And certainly females are capable of conflict. I just think it's a gamble worth taking if you could actually do it. You can certainly find females in history who've done unpleasant things. But nevertheless, we have a very strong evolutionary theory which explains why males benefit more by having conflict and winning conflicts than females do. And so if we want to talk about reducing conflict,
Yes.
then it would reduce it to get rid of males. Now, I understand this is a fantasy, and I think it's a fantasy that people would be able to talk about fairly soon, because reproductive technology is getting to the point where it's quite likely that human females could breed without the use of males. And so there would be a sort of a potential dynamic if everybody just agreed not to have any male babies.
It's a really interesting thought experiment. I will agree with you that if given two buttons, one is get rid of all women, and the other button is get rid of all men, realizing that I have a stake in this choice, you're probably getting rid of all men. If I wanted to preserve Earth and the richness of life on Earth, I would probably get rid of all men. I don't know.
I don't think you have a stake in it. You know, I mean, but you're saying that because you're a man.
Yeah.
But I don't see why being a man should make you any more interested in having a male future for the world than a female future. You know, you've got just as many ancestors who were male as were female.
Mhm. Well, my problem is I'll have to die.
Well, that's going to happen anyway.
I know, but like I prefer to die tomorrow, not today. You know, I prefer to hit the snooze button on the whole mortality thing. But it's interesting.
But this is not suggesting that males have to die in order to make room for females. It's just, you know, you all you have to do is just say, don't let's have any more males born.
Interesting.
Of course, you know, the difficulty is that because we're tribal, you know, some country somewhere would say, well, we're not going to do that.
Yeah.
And then guess what? They'd take over, you
Yep,
know,
they
because
take
they're
over.
males. So that's why it's impossible to imagine it actually happening.
You know what? I'm gonna take that and actually think about it. I don't know. I'm uncomfortable. There's a certain kind of woke culture that I've been kind of uncomfortable with because it's not women necessarily. It's more just there's a lot of bullying I see. There's a lack of empathy and a lack of kindness towards others that's created by that culture. So, but you're speaking about something else. You're speaking about reducing conflict in this world and looking at the basics of our human nature and its origins in the evolution of Homo sapiens, and thinking about which kind of aspects of human nature, if we get rid of them, will make for a better world. It's an interesting thought experiment, worth
But it
thinking
is
about.
only a thought experiment. I mean, you know, it's got no practical meaning right now.
Yes.
And I take your point that, you know, males get a hard rap nowadays in some ways because the balance of social power is moving against, I mean, you know, quite rightly, in a strong sense, of course, against all the nasty things that males do. But what people sometimes fail to remember is that life is very hard for males who don't have the power, who don't have money, who don't have access to women. You know, I'm sympathetic to incels. I'm not sympathetic to them using violence to solve their problems, but I am very sympathetic to the fact that it's not easy simply to be told by well-off feminist middle-class people that you shouldn't behave like this or you shouldn't feel like this, because you do.
Yes. It's who you are. I mean, in general, just empathy and kindness, male or female, I believe will be the thing that builds a better world. And that's practiced in different ways from different backgrounds, but ultimately you should listen to others and empathize with the experience of others and put more love out there in the world. Now that hopefully is the way to reduce conflict, reduce violence, and reduce that whole psychological experience of being powerless in this world, powerless to become the best version of yourself. And that, you know,
Well, no one's going to disagree with all those fine sentiments, right?
but yes, but that's an actionable thing, is actually practice empathy, right? Like saying that somebody should be silenced, or just like this group is bad and this group is good. I just feel like that's not empathy. Empathy is understanding understanding the experience of others and like respecting it. Like, I mean, that's what a better world looks like. That's what the reduction of conflict looks like. It's like, as opposed to saying my tribe is right, your tribe is wrong. Forget the violence or the non-violence part. That act of saying my tribe is right, that tribe is wrong, removing that from the picture, that's the way to make a better world. Like, that's the way to reduce the violence, I think. Not necessarily removing the people who are causing the violence. You have to get to the source of the problem. And I don't mean the evolutionary source, but the mindset that creates the violence is usually just a lack of empathy for others.
Yeah, but I mean, you can't just teach that, because our evolutionary psychology puts us in particular directions.
So do you think it's possible to learn through practice to resist the basics of our evolutionary psychology, the basic forces?
Yeah, I mean, lots and lots of training, lots and lots of education can do it. The famously most peaceful society that anthropologists have recorded involves a tremendous amount of teaching, including some punishment. It's a society in Thailand.
Mm-hmm.
You have to beat it out of children to make them nice.
So it's carrot and stick.
The point is that you do not find societies in which people are spontaneously showing the kinds of behaviors that we would all love them to show.
It requires work.
It requires work.